Welcome back. So we're continuing our quest to try to figure out Lewis dot diagrams. And we're kind of taking these little baby steps. So on this worksheet, what we have to do is draw sort of like electron dot diagrams of ionic bonds and covalent bonds. Now to be clear, you're pretty much always going to be drawing Lewis structures of covalent bonds, molecular compounds. But this diagram here is just sort of to illustrate the idea of valence electrons. So let's look at this real fast. Here we have sodium. It has one valence electron. Here is chlorine. It has 7. And we see that basically this one electron is transferred between sodium and chlorine. And then they form cations and anions. And then down here we see a different example where we have calcium. And if you don't know the valence electrons, yet again, go to the periodic table and you can see that everything in group 1 has one valence electron. Group 2 has 2. Group 3 are 13, 3, 4, 5, 6, 7, 8. And we normally skip these transition metals because of those d orbitals that can really confuse people, and there's some exceptions in here. So calcium's right here, it has 2. So we see that they put 2 dots by calcium. And we have chlorine yet again. In this case, we have 2 chlorines and 1 calcium. So you see that this calcium is actually giving 2 electrons up. It's giving 1 to this calcium and 1 to this calcium. And then they sort of put the ionic compound over here, but they put the charges on it. So you would never really kind of write this way. This isn't a dissociation equation, and this really isn't the proper way to write it, but it's there to illustrate the point. So let's see if we can do some of these ourselves. We have K, potassium. Well, that only has 1 electron. Now keep in mind you can put 8 electrons around these. Each electron is a dot. You can only put 8 because that's how many will be in the outer energy shell if you have a full octet. And normally when they're counting electrons, they're counting the s and the p orbitals, not really the d orbitals, because the s and the p orbitals will be on the outer energy level depending on how it fills. Okay, well, we have fluorine, and it's going to have 7. 1, 2, 3, 4, 5, 6, 7. So visually, this makes sense. We can say this 1 electron is going to go here. And then what you're going to end up with over here would be a potassium that is a positively charged cation and a fluoride, which is negative. And this is a 1-to-1 ratio. We have 1 potassium for every 1 fluoride. Okay, moving down to magnesium. And it has 2 valence electrons. And iodide, or iodine, which will become iodide, which is a halogen. Fluorine, chlorine, bromine, iodine. 7. And then you get in touch with your inner Bob Ross and just sort of make these little dots. We have 7 valence electrons. Well, now we have a problem. This will lose 1 over here, but where's this other one going to go? So we're probably going to need another. I'll have to draw it over here now. Iodine. And you're probably thinking, well, why doesn't it just stop? You know, it gave up 1, so iodine is happy. The problem is magnesium's not happy. It wants to give up the other one so it can become like a noble gas. So both of them have to be happy. It's kind of like a relationship in life. You both have to be happy. Okay, so now we have it. Of course, what's going to happen here? And I'm always writing the metal first because that's what you would normally do. So this magnesium is going to be a 2 plus. And now we have 2 iodides. but we have two of them. And those iodides are both going to be 1 minus. Okay, beryllium. If I go over to beryllium, it's in group 2. And then we have sulfur here. So if we go to sulfur, it has 6 valence electrons. 1, 2, 3, 4, 5, 6. And this is easy because now this is like, hey, bro, take this electron. Take this electron. And yet again, I'll write that metal first. The metal will be 2 minus. Yet again, it's 2 minus because it's getting, 2 plus. It's 2 plus because it's getting rid of 2 electrons and it has more protons. That's why that is 2 plus. Plus the sulfur. The sulfur is actually a 2 minus. Yet again, it's a 1-to-1 ratio. And remember, these are actually solids. These are crystal structures. They form crystalline lattices. And so these numbers here are just sort of ratios of how many cations and anions you have in these crystal structures. You really just don't have, you're not going to find 1 and 1 sitting there. They're going to be in these solids. All right, sodium, our good old friend. Sodium, 1, and oxygen. We see the oxygen has 6. In class, a lot of kids are really confused on this worksheet. And I can kind of see why, because it's sort of a weird worksheet, but I think it does have some value here. So yet again, sodium's like, hey, take this 1 electron. But now we got a problem. Sodium's happy, but oxygen is not. So we're going to need another sodium to come in here and give up another electron. And then we'll have these sodiums, we'll have 2 of them, and they're both going to be a positive charge. We'll have the oxygen, which will be a negative. Aluminum. Well, they probably threw in aluminum because aluminum has a +3 charge. It always has a +3 charge. Just like remember, zinc is always a 2 plus, and silver is always a 1 plus. So aluminum has 3 valence electrons. 1, 2, 3. And then bromine. Isn't it like the happiest element, bromine? It's like, hey bro, I'm bromine. I don't know, just seems like a happy element. So bromine has 7. Notice how they're giving us a whole lot of halogens here. 1, 2, 3, 4, 5, 6, 7. Then you're like, what the, how is this going to work? All right, it's going to give up 1. Well, obviously we're going to have 2 more of the bromines. 1, 2, 3, 4, 5, 6, 7. It's going to give up another one. Now we're running out of space. And chemistry teachers never put enough space in these things, so it's going to look all bad. And then, so it's going to give up another one. So what we have here is Al. It's a 3 plus charge. And the good old bromine, the happiest element, the friendliest element, I guess it likes to make friends because it's a halogen also. There's 3 of them, and it's a minus. Now we got silver. Remember how I just said that silver is a +1 charge? So we do know that it has 1 valence electron. And oxygen has 6. See, it's 6. 1, 2, 3, 4, 5, 6. So yet again, we're going to need 2 silvers. Bam. And if I look at this, I'll have Ag2. Silver will be a positive, and I'll have that 1 oxygen. Okay, that's easy enough. That's ionic compound. A little bit of review. Now we go over to covalent. Let's see what's going on here. Well, covalent, they're not giving electrons away. They're sharing electrons. That's the big difference. See how they're overlapping? So hydrogen has this 1 valence electron, and chlorine has 7. So hydrogen could use 2, If it has 2, it will have a full energy shell, and chlorine could use 8. So they'll just overlap. It's like a Venn diagram where it counts for both. So that electron is now counting for both chlorine and hydrogen. See how they're sharing this electron here? And hydrogen has 2 electrons in its outer shell, and chlorine has 8. So let's see what we can do down here. Notice these are all nonmetals. Covalent bonding happens between nonmetals on the right-hand side of the periodic table. So if you have metals and nonmetals, that's ionic bonding. That's a big difference you need to understand. So first of all, let's just put the valence in. We have hydrogen has 1. All right, plus hydrogen. And here's the thing. I don't really like to draw these little circles because I think that is going to get confusing. So what I tend to do is just draw this line. And this is actually how we're going to draw Lewis structures in the next video. This line represents 2 electrons. It's that one for hydrogen and the one for the other hydrogen. And what that means is this hydrogen, 1, 2, has 2 valence electrons, and this hydrogen has 1, 2, 2 valence electrons. If you want to draw a little circle and overlap them, you can do that. So let's look at fluorine. It's diatomic. Now that has 7. 2, 3, 4, 5, 6, 7. Plus fluorine, 1, 2, 3, 4, 5, 6, 7. Okay, yet again, the first thing you do is just draw your elements and connect them. That's going to count for 2. And now I'll just draw the other electrons around it. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what are we really saying here? These 6 electrons plus 1, 2. That means this fluorine has 8. That's an octet. This has 1, 2, 3, 4, 5, 6, 7, 8. That's an octet. So they're sharing these electrons here. That's a covalent bond. That's a single covalent bond here and a single covalent bond here. There's one up here also. You can do double and triple bonds, so they could share 2 or 3 electrons. Let's go down here. Oxygen. We know it has 6. 2, 3, 4. Plus another oxygen. Well, think about this for a second. This is actually going to have to be double bonded because they want 8. So I can bond it like this. All right. And I could also bond it with another bond. That's 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8. And let's count up how many electrons we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 here. We can never have more electrons over here than here. So we have 6 here and 6 here. So we started out with 12 electrons. We ended up with 12 electrons. See that? And I bonded 2 of these. So why did I do that? Because they now have a full octet. See this? This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That's why you would have to go to double or triple bonds to fulfill the valence octet. All right, nitrogen. Nitrogen's interesting. Let's look at nitrogen. Nitrogen only has 5. So you're starting to see a trend here. This had a single bond. Fluorine and fluorine was a single bond. This oxygen and an oxygen was a double bond. Maybe this is going to be a triple bond. So there's 1, 2, 3, 4, 5, plus 1, 2, 3, 4, 5. And yet again, you would say, well, we have 10 electrons starting out. Let's just bond them and see what happens. That's 1, 2. Well, I could put 4 more over here. 1, 2, 3, 4. 1, 2, 3, 4. But I have a problem. This only has 6 electrons around it. This only has 6. They don't have the octet. That's when you then go to the next. Let's do another bond, see what happens. All right. Well, now this nitrogen has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That doesn't seem to be working. So this one only has 7. So now we're going to have to get a whole nother electron out here. Oops. It's kind of hard to erase that. Put another bond. 1, 2, 3, 4, 5, 6, 7, 8. There we go. The magic number. This also has 8, so there's a triple bond. Alright, now we have CO2. Well, normally you put the least electronegative element in the middle here. Carbon is actually less electronegative than oxygen. So the oxygen's probably going to be in the middle. Then we'll have, the carbon will be in the middle. Then we'll have the oxygens on these sides of this. Now let's just count up the valence electrons first. This oxygen has 6. But it's 6 times 2 because there's 2 of them. So there's 12 electrons there, and the carbon has 4. So in actuality, we have 16 valence electrons between these 3 elements. So the first thing we're going to do is draw a bond between all of them. So we have 1, 2. All right. Then, so now we only have 12 electrons left. You would start fulfilling the valence in the outer element. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that was 1, 2, 3, 4, 5, 6. We're down to 6 electrons. We'll put those 6 over here. Now, this looks good, but there's one problem. Carbon only has 1, 2, 3, 4. It doesn't have 8. These are happy, but carbon is not. And that's when you would go to draw a double bond. So we will erase 1 here and 1 there. And we will double bond them. So we have 1, 2, 3, 4, 5, 6, 7, 8. Oops. Didn't erase the other one there. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. How many electrons do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's how many we started with. We don't have more. Everything has 8. So this is actually a good structure. H2O. Well, we're going to have this oxygen and probably these hydrogens. Here's the interesting thing about this. Hydrogen only has 2 valence electrons. It cannot have more. Because if we look at this period, everything up here only has a maximum of 2 in its outer energy level. So this hydrogen is already happy. It has 1, 2. This hydrogen's happy. It has 1, 2. But this oxygen is not. So this oxygen right here actually started out with 6 valence electrons, and the hydrogens had 2. So we should have 8 valence electrons total. So we have 1, 2, 3, 4. So now we're going to have to draw 5, 6, 7, 8. I could draw these down here also, but I'll go over this later in a different video. I can't draw these electrons on these hydrogens. That's why I went to the central element here, the central atom, because these already have full valence shells. There's nothing I can do. I can't draw double bonds here, so I have to just put them around the central atom, and it works because now this has 8 and these have 2. Okay, well that's a real brief introduction to valence electrons, electron dot structures, and Lewis diagrams. So next video we're just going to do Lewis diagrams. We're just going to start practicing. So I hope that helped. Later.